Welcome back to Wonder and Wonder, the logic of travel adventure. Today, we are diving into a sun-soaked beach and a mind-expanding trip to a local museum. But first, let's mix a bit of philosophy into our fun. Today's theme is representing compound statements. What are we waiting for? Let's go! But why do we need to represent statements? Well, representing statements is the first step in your study of valid and invalid argument forms. Here, we use a single capital letter to represent a simple statement, and we have four connecting words also known as logical constants. Let's kick things off with conjunction. This symbol represents and, which conjoins two statements. For example, I am going to the beach and I am going to the museum. Now, how do we present the logical structure of this statement? We will use a capital letter for each statement. In this case, I will use B and M for going to the beach and going to the museum respectively. Then, put the conjunction symbol. Now, this is read as B and M, or I am going to the beach and I am going to the museum. Next up is alternation. This symbol represents either or. This compound reads either B or M, or just simply B or M. Either I'm going to the beach or I'm going to the museum. Moving on, we have conditional. This symbol represents if then, which is read as if B then M, or if I'm going to the beach then I'm going to the museum. Our last logical constant is biconditional. This symbol represents the connecting word if and only if, like B if and only if M. I am going to the beach if and only if I am going to the museum. Now that we've discussed the four logical constants, I will now introduce you to negation. Let's try negating statements. This is read as, it is not the case that B, if and only if M, or it is not the case that I am going to the beach if and only if I am going to the museum. This is read as, it is false that B and M, or it is not true that I am going to the beach and the museum. Always remember to put a bracket if you want to negate the whole compound to avoid confusion. Now that we know all about logical constants, it's time to dive into Module 3, the truth values of compound statements. Let's begin! We have three principles governing the truth values of statements: the principle of identity, the principle of excluded middle, and the principle of non-contradiction. The principle of identity guarantees that the truth values are more or less stable over time. For example, we use the letter P to represent the statement, puppies are young dogs. And you know that puppies are indeed young dogs by definition, so if P is true, then P is true, which leads us to our next principle, the principle of excluded middle. This guarantees that the truth value of any statement like P is either true or false only. The last principle is the principle of non-contradiction. This will prevent you from assigning two truth values to a statement at the same time and in the same respect. This table reflects the following truth-functional relationship. If P is true, then not P is false. And if P is false, then not P is true. Remember that P cannot be true and false at the same time, but it can be denied twice. When a statement is denied twice, it implies its affirmation. This is the truth table of the negation of compound statements. Always remember to put brackets appropriately to avoid confusion. And since we saw the truth table for the negation, I will also show you the truth table for the logical constants. You can see in this truth table that the conjunction is true only when both conjuncts are true. For alternation, the compound statement is false only when both alternants are false. All other truth values combinations of alternation is true. Now, how do we determine the logical form of a conditional? Take a look at this table. Here, you will see that the conditional is false only if the antecedent P is true and the consequent Q is false. Lastly, the truth table of biconditional. Notice that a biconditional is true only under two conditions, namely, when both elements P and Q are true or when both elements P and Q are false. And that's a wrap for today's episode of Wonder and Wonder. Don't forget to like and hit that subscribe button, and I'll see you on my next adventure. Bye!
Hey there, Logic Warriors! So, welcome back to the channel. Today we'll be diving deep into modules 4 and 5, where we'll be leveling up our skills in logical representation of arguments and basic deductive argument forms. This journey is all about the art of isolating logical structures from their content. Not only is this skill crucial for evaluating argument validity, but it's also essential for advanced proving methods like the truth table. So gear up and let's power up our logical skills. Let's jump right in. So, representing statements and arguments. Understanding how to represent statements and arguments is fundamental to logical analysis. And we have two types of statements. First up is simple statements. These are your straightforward direct representations. For example, the sky is blue. Then we have compound statements. These require us to isolate their logical structure to understand them better. For instance, if it rains, then the gown will be wet. This has a conditional structure. And revealing the logical structure allows for easy determination of validity. Moreover, mastering this technique is essential for assessing deductive argument validity based solely on logical form and not the content itself. Now that we have grasps on the types of statements, let's now move on to effectively representing an argument. To do that, follow these steps. First, identify statements. An example of this is example argument premise 1. If we can represent statements, then we can represent arguments. And to do that next is to use conventional symbols. In logical representation, letters symbolizes statements and their relationships. This method simplifies complex arguments for clearer analysis. The common letters used in logical representations are first capital letters, typically used for simple statements like A, B, or C. For example, A could represent it is raining. Next, we have italicized letters. Sometimes italicized letters denote specific types of statements or emphasize their roles in an argument. Last step is to apply logical conventions. Use 3 dots, for example, to indicate therefore before the conclusion. But keep in mind these important considerations. First is to differentiate between argument, structure, and form. Then, you need to focus on logical relationships rather than the content when doing this. And lastly, practice isolating logical structures from various argument types. If you consider this, you may be a master in logical representation. Now let's explore on how we examine an argument's logical form to determine its validity. Logicians inspect this form to assess whether an argument is valid or invalid. So let's analyze a valid argument structure. The first premise establishes that if R is true, then A must also be true. And the second premise confirms that R is indeed true. From these two premises, we can logically conclude that A must be also true. This structure is valid because it follows the form of modus ponens, a fundamental rule in deductive reasoning. Let's try a practical example of logical structure. Let's take this real-world example. Premise 1. If we study logic, then we improve our reasoning power. Premise 2. We study logic. Conclusion. Thus we improve our reasoning power. And here's the symbolic representation of this example. S equals to study logic and R equals to improving reasoning. When examining the components and validity of this argument structure, we can tell that both examples have the same logical structure. And the first premise states a conditional, and the second premise affirms the antecedent of that conditional. The conclusion is deducted from these two premises. This structure is valid if it meets these criteria. So validity in logical arguments. Understanding what makes an argument logically valid is paramount, as validity means that if the premises are true, the conclusion must also be true. And a valid argument has no case where true premises leads to a false conclusion. Thus, content does not factor into validity assessment. And we have two key terminologies, modus ponens and modus tollens. Modus ponens is a fundamental rule of inference in propositional logic, often referred to as affirming the antecedent. It allows one to derive a conclusion from a conditional statement and the affirmation of its antecedent. And modus tollens, on the other hand, is a rule of inference that allows one to conclude the negation of the antecedent when the consequent of a conditional statement is denied. Now, let's explore an example of an invalid structure. First, premise 1. If we study logic, then we improve our reasoning power. Good. Premise 2. We improve our reasoning power. Conclusion. Therefore, we study logic. Here's the symbolic representation of this example. So in this case, the first premise states that studying logic leads to improved reasoning, which is good. And the second premise asserts that reasoning has improved. Kinda iffy. However, concluding that studying logic must have occurred is invalid because other factors could lead to improved reasoning. Now let's take a look at how valid and invalid arguments stack up against each other. In terms of structure, the arrangement determines if it's logically sound. You just need to analyze it. And in the first premise, it establishes a condition. They both do that. However, in invalid ones, it may mislead by suggesting a false premise. And in the second premise, on the other hand, this either supports or contradicts. Affirming the antecedent leads to validity, while affirming the consequent leads to invalidity. And in terms of conclusion, it must logically stem from its premises. If it does not follow logically from its premises, it is an invalid argument because it can create confusion to the reader. We have mentioned in a previous slide that affirming a consequent leads to invalidity, and this is called the fallacy of affirming the consequent. This fallacy occurs when one mistakenly concludes that if the consequent is true, then the antecedent must also be true. And constructing a truth table for this type of argument reveals the instances where true premises lead to false conclusion, rendering it invalid. Let's now move on to addition structure. Addition structure is a logical structure where some arguments are valid and some arguments are invalid. Therefore, some arguments are valid and some arguments are invalid. And to represent this type of structure, we use the symbol V for represents valid and I for invalid. The argument structure looks like this. This structure illustrates that there can be both valid and invalid argument within a set of statements. It emphasizes that not all statements can be categorized as strictly valid or invalid. Some may fall into both categories depending on the context. Now we have discussed Module 4 thoroughly, let's now transition into Module 5. Good job for making halfway through our discussion. This module builds upon of what we've learned by introducing basic deductive argument forms. Before diving into new content, let's take a moment to explain some key symbols that will guide us through this lesson. For the arrow symbol, this symbol represents a conditional relationship. Think of it as saying if we can represent statements, then we can represent arguments. It sets up a cause and effect scenario between two statements. Next, we have the therefore symbol. This symbol stands for therefore. As the name suggests, it introduces a conclusion drawn from the premises, like saying, therefore we can represent arguments. Next is a bullet point symbol. This symbol symbolizes conjunction, meaning and. It joins two true statements together. For instance, amphibians are animals and birds have feathers. Next, we have a lowercase v. This indicates disjunction, meaning or. You could say whales are mammals or snakes are reptiles, showing that at least one statement must be true. And we have the not symbol. This symbol represents negation, indicating that a statement is false. For example, if P represents it is raining, then not P means it is not raining. Now that we've equipped with these symbols, let's move on to our objectives for this Module 5. Let's kick things off with conjunctions. Conjunction involves joining two true statements to preserve their truth value. An example of this is first statement A, amphibians are animals, and statement B, birds have feathers. To represent this conjunction, we use A dot B or A and B. Conjunction is fundamental in logical arguments because it allows us to combine true statements into more complex yet valid arguments. Because if both statements A and B are true, then their conjunction A and B is also true. Next up is simplification. Simplification allows us to separate conjuncts while preserving their truth values. Let's take A and B for example. A and B can be deduced to either A or B as true. It is represented by A and B, therefore A, or A and B, therefore B. This process is considered valid in logic because if both A and B are true, it is logically following that either one can be considered independently true. Now let's talk about alternation. Alternation involves creating an alternative conclusion from two true statements. Let's take W, whales are mammals, and S, snakes are reptiles in this example. This can be represented as therefore W vs or therefore whales are mammals or snakes are reptiles. It is important to note that while you can infer conjunctions from two statements, you cannot infer alternants from an alternation. Doing so can lead to an invalid structure. Keep that in mind. Moving on to disjunctive syllogism. Disjunctive syllogism allows you to conclude one disjunct when the other is negated. Let's take the example P or Q. If we say that it is not P, therefore it is Q. This means if P is false, then Q must be true. That's simple. Now let's look at invalid argument structures. First, we have subtracting an alternative. An example of this is R v L or R or L. You cannot infer either R or L independently because both conclusions could be false. This structure illustrates that you cannot infer any alternant from an alternation. Doing so leads to an invalid conclusion. Next up is denying an alternative. This involves incorrectly concluding that if one alternative is false, the other one must be true. Let's take the example P or Q. If it's said that it is not Q, it is invalid to already conclude that therefore it is P. Because this reasoning is flawed because just because Q is false doesn't mean P has to be true. But isn't this similar to disjunctive syllogism? Yes, but they vary in validity, logical structure, and error in reasoning. In denying alternative, it is invalid because it incorrectly assumes truth of the other disjunct, and it also assumes exclusivity without justification. Finally, let's discuss adding a conjunct. You cannot infer that adding another statement must also be true if one statement is already known to be true. Let's take the example, therefore P and Q. If we know that P is true, we cannot directly say that Q is also true without further evidence. This highlights the importance of not assuming additional truths without any justification. Modules 4 and 5 provide essential knowledge for understanding logical representation and basic deductive forms. Mastering these concepts will enhance your ability to engage in sound reasoning across academic and professional contexts. If you found this video helpful, don't forget to smash that like button and subscribe for more awesome content on logic. Until next time, keep leveling up your logic skills, Logic Warriors. Bye-bye!
Welcome back to my channel. Get ready with me as I discuss to you things about Modules 6 and 7, starting from complex argument forms. So let us dig deeper to the concept of modus ponens. It says that if you have a conditional statement, if R, then L, which can be seen in the PowerPoint. Premise 1, if R, then L. Premise 2, R, therefore L. And if we use it in an example, if it rains, then the ground will be wet. Premise 2, it is raining, and therefore the ground is wet. From here, we can see that the premise 2 affirms the antecedent. On the other hand, affirming the consequent is the reverse in an invalid argument. Premise 1, if R, then L. Premise 2, L. Therefore, R. Next, the opposite of modus ponens is modus tollens, from which is simply the negation of the antecedent from a conditional statement and the negation of the consequent, which the structure looks like. Premise 1, if R, then L. Number 2, not L. Therefore, not R. Which, if we use it in an example, premise 1, if it rains, then the ground will be wet. Premise 2, it is not raining. And premise 3, therefore, the ground will not be wet. Formal logicians say that modus tollens is valid when denying the consequent or the then statement, while modus ponens is valid when you affirm the antecedent. However, when you do the reverse, such as affirming the consequent and denying the antecedent, you create an invalid argument in the form of premise 1, if R, then L. Second premise is not R and therefore not L, which is called denying the antecedent. Remember, when you affirm the consequent and deny the antecedent, the result is an invalid argument. Moving on, another invalid argument is detaching the consequent in the form of if R, then L. Premise 2, therefore L. You cannot infer the consequent because the consequent and the antecedent of a conjunction can both be false, yet the conjunction can still be true. Moving on to a more complicated and valid reasoning argument is hypothetical syllogism. Premise 1, if R, then L. If L, then C. Therefore, if R, then C. So let's take a look at an example. Premise 1, if it rains, then the ground will be wet. Premise 2, if the ground is wet, then the flowers will grow. And premise 3, if it rains, then the flowers will grow. Next is the fallacy of misplaced middle. This fallacy is committed when the middle term is not shared properly in either minor or major premises. An example using this is, all cats are mammals. All dogs are mammals. The middle term mammals fails to establish a direct relationship between cats and dogs. Another concept is constructive dilemma. It is another example of a complicated valid argument. Premise 1, R or L. Premise 2, R then D. Premise 3, L then C. And therefore, D or C. It is a combination of two modus ponens. So, using it in an example, if it rains, then the picnic will be cancelled. If it is sunny, then we will go to the beach. Either it rains or it is sunny. Therefore, either the picnic will be cancelled or we will go to the beach. On the other hand, destructive dilemma is a combination of two modus tollens, which we can see in the PowerPoint. There are two conditional statements and concludes that both options cannot be true, leading to the negation of both premises. Let's move on to two fallacious forms of dilemma. First is pseudo-dilemma 1. It simply commits the fallacy of denying the antecedent, which structures as R then D, number 2, L then C, premise 3, not R or not L, and therefore not D or not C. Pseudo dilemma 2, the structure is as shown. This one is an invalid argument as it affirms the consequent of premise 2 and 3. But our norm again is affirming the antecedent or denying the consequent of a conditional. Moving on to module number 7, constructing a truth table method. In here, we are going to determine the validity or invalidity of any argument form in the terms of truth table method. First step is representing the argument in horizontal form, like what is shown in the PowerPoint. Second is counting the number of simple statements in the argument. In here, we have 2, the R and the L. Third is constructing a table for all the possible substitution instances of the truth values of R and L. Fourth is assigning the truth values to the statements in an argument structure. You can see that no matter how you change the truth values of the statements in the argument remains logically correct. Next, we have an invalid form of affirming the consequent which has the same 4 steps earlier. But there is a situation that shows where the premises are true, but the conclusion is false. Therefore, the argument form is invalid. Valid or invalid is only to use for argument forms and not individual arguments. We focus on the overall structure of the arguments rather than specific examples. Next, the shortcut method is the falsification method. This is only needed when dealing with 3 or more statements. Remember that your intention is to falsify the conclusion while retaining the truth of both premise set like this. You begin your analysis from the conclusion. If P or R is false, this means that both P and R are also false. If the premise set is true, this means that both alternation P or Q and Q or R are true. If P and R are false, the same value should be assigned to P and R in the premise set. Thus, you are left only with Q. Notice that whatever the value of Q, either true or false, you have discovered a row where the premise set is true and the conclusion is false. The argument form, therefore, is invalid. Remember that only one example of a horizontal where the premise set is true and the conclusion is false is sufficient to judge an argument form to be invalid. That's it for today's video. We hope you enjoyed watching and learning. See you on our next one. Bye!